Today we're going to talk about rates of change. Now you've done a lot with rates of change, whether or not you've realized it. So rates of change can be thought of as speed, for example. So every morning I get up, I walk to school. It's not very far. I only live, I don't know, half a mile or so. So let's say that I walk at a constant rate. As soon as I leave my house, I'm going a particular speed, and I continue that speed until I hit the school. Run right into it. So let's say that my speed is 8 feet every 1 second. 8 feet per second. So if I were to graph or make a chart of my position, I could say my x values are going to be seconds, and my y values are going to be feet. So at 0 seconds, I haven't traveled at all. 1 second, 8 feet, 2 seconds, 16 feet, 3 seconds, 24 feet, and so on. The graph of this, as you well know, is a linear equation. So my x-axis is graphed in seconds, and my y-axis is graphed in feet. So my first point is 0, 0. I haven't traveled anywhere. 1 second into the story, I've now traveled 8 feet. 2 seconds into the story, I will have traveled 16 feet. And you can see, if I were a good artist, that that is a straight line. And my speed is constant. Anytime you have a linear equation, the speed is constant. So at any point, I'm traveling 8 feet per second. Well, let's say that the next day I get up and I'm really tired, so I start walking to school, and I look at my watch and I notice that I'm late. And I realize I'm late, and so I decide to start speeding up. So I'm really tired. I start going, and I realize I need to speed up, and I speed up faster and faster and faster. By the time I get to school, I'm sprinting. Well, you can see that near the bottom of this graph, the steepness is not very big. It's really shallow, we would call it. So my speed during that time is low, and the longer the story progresses, the faster I end up going. And you can see maybe right here, I'm going as steep as I am there. So that could be 8 feet per second, but then I go faster and faster and faster. And up here, I might be going, I don't know, 20 or 30 feet per second. I'm running as hard as I can. Now, finding the speed at a particular moment. So if I wanted to know exactly how fast was I running 10 seconds into the story, we call that calculus. If you want to know the speed at any particular point in time, which is called the instantaneous rate of change, if you want to know that, you have to use calculus to get it. In fact, half of calculus is based on finding the speed at a particular point. That's half the class. And it's really not too hard to do, but there's a lot that goes into it. So we're going to leave that alone. We're going to say instantaneous rate of change is for the calculus students. What we want to know is, what is the average rate of change? So, for example, let's say I wanted to know between seconds 2 and 3, how fast were you going on average? So right at 2 seconds, I was going kind of slow. I slowly sped up until 3 seconds, I was going faster. Well, how much ground did I cover in those 3 seconds? So all you really need to know is the slope of this line. And you can see that the graph is a little bit underneath the slope. But let's say that at 2 seconds, I was at 3 feet. So 2, 3. So 2 seconds into the story, I had traveled 3 feet. Well, 3 seconds in, I traveled 7 feet. So 3, 7. Well, that means that in 1 second, I traveled 4 feet. So my average rate of change would be 4 feet every 1 second, or 4 feet per second. Now, When I was at 2 seconds, I was traveling slower than 4 feet per second. You can see that this line is not as steep at 2. And then when you get up to 3, the graph is a little bit steeper. But this 4 feet per second is the average rate of change between 2 and 3. So it took me 1 second to go from 2 to 3, and in that time I traveled from 3 feet to 7 feet, so I gained 4 feet. So the slope of that line between the 2 points is just the average rate of change. So between 2 seconds and 3 seconds, I averaged 4 feet per second. And that's all the average rate of change is given an interval of time, how much ground was covered in that time. So let me show you another example. Open up your textbooks. Let's look on page 109. Average rate of change. So the top of 109 says, it defines average rate of change. It's a function over an interval in the ratio of the difference, the change, in y over the difference in x. Now, these little symbols, they're Greek letters from the Greek alphabet. They're deltas, and we use them a lot in calculus. Delta y means the change in y, how much y changed, and delta x is how much x changed. And you've seen this formula before. It's just the slope formula. So if you want to know the average rate of change over a particular interval, all you need to do is find the slope between those 2 points, and that will tell you the average rate of change. So, example number 1. Find the average rate of change for 2/3 roots of x plus 3 on the interval -3, 5. So if I had my chart, my x's and my y's are going to be -3 and 5, and I just need the y values associated with those x's. So I'm going to plug the x's into the equation. So let's plug in -3. 2/3 roots of -3 plus 3. Well, -3 plus 3 is just 0, and the third root of 0 is 0, and 2 times 0 is 0, so -3 comma 0. Now I need to plug in 5. So 2/3 root of 5 plus 3. Well, that's 2/3 root of 8. What number times itself is 8? The third root of 8 is 2. So this is 2 times 2, which is 4. So at -3 seconds, the position is 0. 0 feet, for instance. At 5 seconds, the position is 4. So the average rate of change is the slope between those 2 points. And they've given you the graph. So you can see this graph here. And there's the point -3, 0. And here's the point 5, 4. So to find the slope, I just need to do y, the second y minus the first y, divided by the second x minus the first x. So the second y is 4 minus 0 over 5 minus -3. So I get 4 over 8, which is 1/2. Which means, on average, I'm traveling at 1 foot per every 2 seconds. So 1/2 a foot per second. Now the really crazy thing about average rate of change is, if the function touches those 2 points, the average rate of change is always going to be the same. So if I had another graph, so we could do the old tortoise and the hare story. Let me zoom in on this a little bit. So let's say that this is a graph of the tortoise racing the hare. So if the rabbit starts running really fast and then slows down, and it gets to 4 at 5 seconds, and let's say that the tortoise starts really slow and speeds up, what is the average rate of change? Well, because they started and stopped in the same place, the average rate of change is exactly the same for both racers. even if it was a straight line, if somebody went at a constant rate, that average rate of change would be the same. And let's say that somebody ran forward, turned around, ran backwards, went past the starting line, ran forward, past the finish line, and then ran back there. The average rate of change is exactly the same. So we have 4 different runners, but because 3 seconds ago they were at 0, and in 5 seconds they're at 4, the average rate of change is exactly the same. If you were to take all of their positions and average them out, you would get that average rate of change. So your assignment today is on page 111. So let's look at number 1. So I want the average rate of change on the interval -1 to 3. So my x's are -1 and 3, and then I just need to find my y values. Once I find the y values, then I do y2 minus y1 over x2 minus x1. Okay? So I need to plug in -1. So I put -1 in there and in there. 3 times -1 times -1 is 1, minus -1 plus 5. So I have 3 times 1 is 3, -1 is just plus 1, plus 5, 3 plus 1 is 4, plus 5 is 9. So -1 comma 9. All right? Now I need to plug in 3. So 3 times 3 squared is 9, minus 3 plus 5. So 3 times 9 is 27. 27 minus 3 is 24. 24 plus 5 is 29. So now I have my 2 points. Subtract my y's. 29 minus 9 is 20. Subtract my x's. 3 minus 1 is 2. 20 divided by 2 is 10. So my average rate of change is 10. That's the slope between those 2 points. Okay? So let's look at number 2. So I need to plug in -3. So 4 times -3 times -3 is 9, plus 12 times -3 is -36, plus 9. So that's 4 times 9 is 36, minus 36 plus 9 is just 9. So my first x is -3, and my first y is 9. My second x is 0. So I plug in 0. 0 squared is 0. 12 times 0 is 0, plus 9. Y equals 9. Well, this rate of change is a little bit strange. It says at 3 seconds, I was -3 seconds, I was 9 feet from my house. At 0 seconds, I was also 9 feet at my house. So what's my average rate of change? And the answer is 0. If I perform the slope, 9 minus 9 over -3 minus 0 is 0 over -3, which is 0. So as far as the average rate of change is concerned, I didn't move. 3 seconds ago, I was standing at foot number 9, and right now I'm also at foot number 9. So my average rate of change says I didn't move at all. My average rate of change is 0. If we were to graph that, that might not really be true. So 3 seconds ago, I'm up at 9. Right now, I'm up at 9. I might have walked backwards and then walked forwards, or I might have done something like this, or I might have done something like this, or I might have just stayed there. I don't know, but overall, If you were to add up all of my speeds at every possible moment, added them up and taken the average would have been 0. Some of them were positive speeds, some of them were negative speeds. Well, I guess velocities. But overall, I didn't move, so my average rate of change is 0. Okay? Number 3, they try to be really tricky on you. And they say, okay, here's the function. Start at 3 seconds and end at a seconds. And we can be sure that a is bigger than 3, not that it's going to matter much. So my first x is 3, and my second x is a. So I plug in 3. Negative 3 squared. 3 squared make it negative is 9. 9 plus 4 is 13. So 3 comma 13. For the next one, I'm going to plug in a. And I get negative a squared plus 4. So negative a squared plus 4 is my second y value. And I don't know what a is, but I'm sure it's bigger than 3. It has to be bigger than 3. So I just plug this into my slope formula. Slope formula is y2 minus y1 over x2 minus x1. So my second y is, oh, that's a 4, sorry. Negative a squared plus 4 minus 3 over my second x minus my first x, so a minus 3. So I get negative a squared plus 1 over a minus 3. And I could pull out a negative 1 and factor, but it's not going to simplify. So this is my average rate of change. And if you want to know an exact value, then you would plug in like 4. You could plug in 4 and you could find the average rate of change for that. Okay? I do want to show you one that is negative. So I'll make one up. So let's say we have negative x squared plus 2, and I want to know what is the average rate of change from negative 1, from x equals negative 1 until x equals 5. Okay, so I need my y values. What is the opposite of negative 1 squared plus 2? Well, negative 1 squared is 1, and the opposite of 1 is negative 1, so negative 1 plus 2 is 1. So negative 1 comma 1 is my first point. For my second point, I plug in 5. What's the opposite of 5 squared plus 2? 5 squared is 25. The opposite of 25 is negative 25 plus 2, which is negative 23. For my average rate of change, I do y2 minus y1. So negative 23 minus 1 over x2 minus x1. So 5 minus negative 1, which is really just 5 plus 1. So negative 3 minus 1 is negative 24. 5 plus 1 is 6, which is negative 4. Because that slope is negative, it means that my average rate of change was negative. So for instance, let's say this is a graph of me walking to school, and instead of walking to school, I walk the other direction at the rate of 4 feet per second. So a second ago, I was 1 foot closer to the school than my house. 5 seconds ago, I was 23 feet further from the school than my house. So I was walking in the wrong direction, so my slope is negative. If you were to graph that, it would look like this. So we'd have like that. So you can see that I'm walking in the wrong direction. So that slope is negative. Okay, for your assignment today, I would like you just to do 1 through 24. And in each problem, you're just plugging in both x's to find the y's. and then plug them into the rate of change formula y2 minus y1 over x2 minus x1. When you're done, go ahead and turn that in. We are going to do pages 112 and 113 when I get back, but we'll count that as a different assignment. So all the problems on 111 are your assignment today. As soon as you get that done, go ahead and hand it in.